when you work with linear equations, remember that the degrees of the variables are to the first degree. So here y is to the first degree. It's not squared. I'm not taking the square root of x. Everything is to the first degree. So I could solve for x or solve for y. Often you might have an equation that's something like f of x, and sometimes we interchange that with y. That f of x is telling you that the equation is dependent on x, so x is the independent variable here. So here y is a dependent variable and x is the independent variable, and that's often what you've seen in equations. Now we could write these equations in different ways. I might put everything on the same side. I might multiply everything by 3. That doesn't change the actual equation. Their relationship to each other remains the same. So suppose that I had 1/2 y minus maybe 3/2, and that equals 5/2 or something. If I didn't want to deal with those fractions, I could multiply everything by 2, cancel out the fractions, and that can often help you work with these a little easier. So those are some things to keep in mind. Real world situations aren't always modeled by just one constraint, and so if you have, say, a word problem, or you have a scenario which has more than one constraint, we sometimes use more than one equation. That's what leads us to using systems of equations. A 2x2 system has 2 equations and 2 unknowns. If you have say n unknowns, then you need at least that many equations in order to solve that system. Sometimes you might have more equations than unknowns. That can lead to issues. If you don't have enough equations, for say you had 3 variables and you only had 2 equations, well, that's like not having enough information. So what will happen is you'll never be able to solve for a unique solution there. A unique solution means a single solution for that set. In this set of slides, I'm going to focus on linear equations, and we are going to mainly focus on a 2x2 system. So here I have a 2x2 system. X and y are my unknowns, and I have 2 statements. So they're like mathematical sentences. So I know that this relationship exists on the first line, and the second line, that relationship exists. I'm going to discuss a few different methods to solve systems of linear equations. Fortunately, as a student, there are many different approaches, and I want you to feel comfortable with all of these. Sometimes one may be easier than the other. You don't want to just get stuck and only use one method all of the time, so try to kind of practice different methods in your homework. One method is really piece of cake. If you have technology, graphing is always really easy. Often it's easy by hand, but always a piece of cake if you can graph the 2 equations. These are linear equations, so they're just 2 lines, and if I graph those 2 lines, then I'll be able to solve that system quite easily. Another one, substitution. Now anybody can do these first 2 methods. Substitution, we'll talk a little bit more about that. You've probably worked with that in Algebra 1, and so I'll review this a little bit, but those are always the easiest methods. Another method I'll discuss is elimination by addition. Now that might be somewhat new to you, so I'm going to give you some information to kind of help you with that, and I'd encourage you to practice it. If you haven't done that before, please try to practice that some in your homework, and let me know if you're having trouble with it. And this other method, matrices. So we've barely touched on matrices. I am going to just talk a little bit about how you can use matrices to solve a system like this, but there are other methods. So today I'm only going to discuss using the inverse of a matrix. However, you could also use Cramer's rule or row operations to solve a system of equations. And for large systems, so maybe a 5x5 system, their matrices are usually a little easier to work with than these other methods, and so keeping that in mind, matrices become very helpful when you have a lot of information. Okay, the first method we're going to discuss graphing. Now if you have a calculator, you could pull out a calculator or Desmos. Desmos makes this so nice. So here I have 2 equations and 2 unknowns. I can simply type those in on a calculator. Now yes, if you're working with a TA83 or a TA84, you're going to have to solve for y, and that takes a little bit of work. If you want to do this by hand, often you can just graph them by hand, and that can help you as well. I kind of know that this one doesn't have integer answers really nicely, so I'm going to show you how to do this in Desmos. So I want you to think about this before we type it in. What could happen when I graph a 2x2 system? Since these are just lines in 2D, then those 2 lines, are they going to intersect in more than one place? And if you think about that, they should, since they're linear, they're never going to intersect more than once. They could intersect once, but what other possible outcomes could happen? So I want you to think about two chopsticks. And if I were holding two chopsticks in the air in class, I'd drop them on the floor, and we'd kind of talk about what kind of outcomes could happen. And what I hope that you kind of could see after you've thought about that for a little while, those chopsticks, they could fall and intersect in exactly one place. They're never going to cross more than once. That's not possible because they're lines, but they could intersect in exactly one place. Since I'm wanting all of the x's and y's where both of these statements are true, that point is an ordered pair, x comma y, and it's the point of intersection of those two lines. It's the point, it's the x and y in which both of those are true, and so that would be our solution. So a solution to a 2x2 system of equations, you're just looking for the point of intersection. And that's actually true when we talk about nonlinear systems as well. So when you're solving a system of equations, you're looking for those points of intersection. Now you could have one point of intersection, or when you drop the chopsticks, there could be some other cases. Like, what if the chopsticks just so happen to lie perfectly parallel on the floor? If those two lines are actually parallel, it means they have the exact same slope. And in that case, those lines are never going to intersect. That kind of a system has no solution. Those lines will never meet. And the last case is kind of strange. What if those chopsticks were to fall right on top of each other? Now, yes, it'd be rare in real life scenario. However, these three cases are the only three possible outcomes when you're solving a 2x2 system of linear equations. And this last outcome, what this means is if these are perfectly lying on top of each other, they have the exact same slope and they're going through all of the same points, and so they're actually the exact same line. If you get these two cases, this is where your information might be a little odd if it is supposed to be modeling a real life scenario. So you might want to go back and look at your information. We're going to talk about a couple vocabulary words really quick. So I just discussed why there could be one solution, no solution, or infinitely many. If there is no solution, so if the system has no solution, we refer to that as an inconsistent system. A real life word problem, if this were to happen to you where the lines were parallel, then you probably have some information that's incorrect in your word problem. This is referred to as an inconsistent system. If you have infinitely many solutions, that's what happened when the two chopsticks were perfectly aligned. They had the exact same slope and were going through all of the same points. In that case, that system is said to be dependent. You really only have one piece of information, so you don't really have two different mathematical statements. Those statements are actually repetitive. You really only have one, and if you have two unknowns, you can't isolate for a unique solution. So we say that those two equations are dependent on each other. So dependent system is what that's what the vocabulary word is saying. It's saying that those two lines are really the same, giving you the same information. Alright, if we graph, so graphing linear equations, since these two lines, the solution, it's just going to be the point of intersection. Now here I have these two lines graphed, and I encourage you to try this on your calculator or Desmos. Desmos actually makes this really friendly. If you'll just open up Desmos, you'll be able to graph these, and you're actually able to click on this point of intersection. So when you graph this in Desmos, I'm actually just typing those in. I don't even have to solve for y. That makes that so easy. And I actually can just click right here on your phone or a touchscreen, and it'll tell you the point of intersection. Now, if you've been practicing in class, we've talked about these patterns in decimals. This 727, I wonder if that's 7272727, and if it is, if it's 0.72 repeated, that would be the same thing as 72 over 99. Or you could divide 72 divided by 9 is 8, so that's really 8 over 11. And because that point was 3 0.727, then I'm going to add this to 3, or you could think of that as 33 over 11, which is the same thing as 41 over 11. And so if you notice there, it looks like their point of intersection is 41/11 would be the x value. This is 0.63. I'm going to go ahead and tell you it's 0.636363. Pause the video and see if you can find that decimal. And once you've taken a minute, you should have tried 63 over 99. If it's 0.636363, that's what we were practicing. And if I divide the top of that by 9 and the bottom by 9, I get 11. So I'm going through this to kind of throw back to some other things we did in class, but this point of intersection is 41/11, comma 7 over 11. That represents an ordered pair where those two lines intersect. And so that's to give you an example of how easy this will be if you use something like Desmos. Graphing, if you're able to use a calculator, which often I don't allow my students to in class because I want them to understand the ideas. Graphing, it's just that easy. You just need to look for the points of intersection, and as long as you type your information in correctly, then it will give it to you. I'm also going to send you some instructions for how to do this on your calculator. I have some of them typed up here, but they may be difficult to read. If you're using a TI-83 or a TI-84, then your method, you'll probably just type in your equations, so you will need to solve for y, and then hit graph. If you go to this option, it's second trace, and select option 5, you'll actually be able to find the point of intersection. You'll move your arrows. You want to get pretty close to the point. Now if they're two lines, to be honest, you don't have to be right on the exact place, but if you get pretty close to the point as instructed, then it'll tell you the exact point of intersection. The cases where you need to be very careful is when we have especially nonlinear equations, and in that case, try to get close enough to the point that you won't confuse the calculator. If it has multiple points of intersection in the interval you give it, then it will probably return an incorrect one. So be careful with that. But this will talk you through the calculator. So make sure you spend some time knowing how to do that on a calculator and the computer. These are often on ACT tests or different standardized tests. The second method I'm going to talk about is substitution. Now substitution anyone can do. Even my students that have a lot of trouble in math can still use substitution. Simple approach. So all we're going to do is solve one of the equations for one of the variables and substitute that into the second equation. You'll notice I have x highlighted here. From the first equation I could solve for x, and then I could plug that into the second equation. Since x, you can isolate x here, you can subtract 4y from both sides, divide by 2. Now remember, this equation is the exact same equation as that. I know they look different. One is dressed up slightly different than the other, but they're the exact same. You could have divided everything by 2 here and written that instead of what I have. So keep that in mind. All I did was rewrite it so that I isolated x. Then I'm going to plug that in for the x in the second equation so that I get a statement something like this. I'm going to simplify that, so just algebraically combine like terms. 15 minus 6y minus 5y, I'll have a minus 11 there, and then equals 8. You'll go ahead and get y by itself, so 15 on the other side gives me a negative 7, and again y is equal to 7/11. So this is the exact same system we graphed, so I should get the exact same answer. Once I get a solution for y 7/11, plug that into this statement where you isolated x, and you'll be able to get x. And again, we do get that ordered pair. Now here I usually ask you a few questions in class. Did I have to solve the first equation for x? No, I encourage you. You could have solved the second equation for x or the second equation for y. There are different approaches. So your work may look different than a friend's. It doesn't mean you're doing it incorrectly. I encourage you to have various approaches to this. Use whatever's natural to you. Also, certain equations might be set up in a particular way where it's easier to solve for one variable than another. This method is always an easy approach. Anyone can do this, and you should feel confident. The thing about this method is often it requires a few extra algebra steps, and it's easy to make little algebraic errors. This can take a long time if this is a bigger system as well, and so those are some pros and cons of this approach. I do suggest that everyone knows this approach. There may be a case where suddenly a word problem is in a really nice form to use this, so you still want to know this method. It can also be useful to check your work. Remember that I don't think I said this yet. I could check my work just by substituting this x and y into the first and the second equation, and I should show that they're identities. So the left side should equal the right side when I plug these x and y in. That helps your confidence because you always know if you got the right answer. The next method I'm going to discuss is elimination by addition. This might be slightly new for you all. I have attached on Google Classroom a worksheet that will help you work this out and have a little bit of notes. I'm again going to use the exact same system, so we know what answer we're expecting here. But this method, it's a little bit different than the other two methods I've discussed. So using elimination by addition, what we're going to do is try to rewrite this system where it's more convenient for us. So remember when I said that 2x plus 4y equals 10 is the exact same equation as x plus 2y equals 5? You could also multiply everything by pi or multiply everything by 1/13. Now, I might not do that if it's not convenient, but they are the exact same equations. What we want to do here is rewrite this system. So rewrite these two equations. I might only need to rewrite one equation, but I rewrite this set of equations so that if I were to add the equations together, one variable would completely cancel. Now, the reason that we can do this is because these two equations, if there is a solution to the set of equations I have here, then that must work for any x comma y. So this works for any real numbers x comma y without any domain exclusions. So I'm able to do this because what we're going to do is eliminate one variable and substitute it back in. This should work as long as the system does have a unique solution. When it doesn't work, then I'll try to go back and talk about that, and you can ask me about it if I don't make time for it in this video. Remember that there are cases where the system could have no solution or infinitely many solutions. So in that case, when you use elimination by addition, some odd things might happen in your outcome, and you'll need to think about what that implies. To begin with this method, so what I'm going to do is rewrite the first equation, and if you'll look at my changes here, it's actually the exact same equation, but I notice I've divided everything in the first equation by 2. That would have left me with x plus 2y equals 5. I've taken that and multiplied everything by -3. So if you take the first equation and multiply by -3 over 2, pause the video and see if you can understand why this is still the same equation. I've used different constants. Once you've given that a little bit of time, I would have asked you in class why I would have approached it that way, and some of you would have yelled out great answers about, well, now I have these -3's out, this -3 and this 3 in front of these x terms. And you'll notice I have this line beneath them. What I'm going to do is take the first equation plus the second equation. Hence elimination by addition. I'm taking the sum of those two rows, and what will happen is because these coefficients in front of x, the sum of those will now give me 0x. I'll cancel out x and I'll be able to isolate the y terms. And so what happens when I add the two rows is I'm given -11y is equal to -7. And again, you'll notice that y is equal to 7 over 11. And if you were to substitute that back in, and someone might ask me in class, where do I substitute back in? Either one of these equations, whichever is easiest for you. So once you get y is equal to 7 over 11, you're going to substitute that back into the first equation or the second equation, whichever is easiest, and that will help you get the x value. Since we already did that before, you can really just use the slide that I had up here before to go ahead and solve for 41/11, but in a regular problem you would still need to go through that. So just to summarize what I've done, this method is called elimination by addition. I've conveniently rewritten the system. I took the first equation and multiplied by -3/2. The reason I chose to multiply by -3/2 is because that would give me a -3 in front of the x on the top row. That way, when I added the two rows together, I would get an equation that just had y. And there are a lot of different approaches you could have taken. You could have gotten maybe 10s in front of the y's on the first row and the second row. So you could have thought about what numbers you needed to multiply the first row and the second row by. You could have multiplied the first row by -3 and the second row by +2, and that would have given you 6's in front of the x's, and that also would have worked. There are many different approaches here, but the main idea is what's very important. So given a system, you rewrite the equations in standard form. That's the form that I have written here. I haven't talked about this in this set of slides, but if you had x's and y's in different places, you want to get them so that everything with the variables, you just have coefficients times variables on the left side is equal to the constant. And that's what helped me in this process. So always get them in standard form first, then rewrite the equations so that one column would easily simplify if you were to add the two rows. Once you get an individual variable by itself, you'll substitute that back into the system to find the second. So this is elimination by addition. Let me know if you have trouble with that, but this is a method some of you have seen, some of you haven't, so I want you to try to practice that in your homework. The last method I'm going to discuss in this video is using matrices. We've discussed matrices a bit. I do want you to use your calculator in this assignment. I want to talk more about how to do this without a calculator, but that won't be in this video. That will come next week. So recall when you did matrix multiplication from the last assignment, it is not commutative. That means that A times B is not equal to B times A when you're using matrices. So in your calculators, you'll need to keep that in mind when you're multiplying things out. You must consider order. Given a 2x2 system, we've practiced writing this as a matrix equation. What we do is we take the coefficients and we write those in a matrix, often called a coefficient matrix. Often we might use A. So A will just be the coefficients from the variables on the left. B is a constant matrix, and it holds this, it's a vector holding these numbers 10 and 8. So as a matrix equation, in this form, you might have something like this. A 2x2 matrix times this column is equal to 10, 8. Those would be my constants. This is not augmented form. In augmented form, that's where we leave out the variables and the equal sign. You may have heard me talk about that. And you can use that form and complete and solve matrix equations as well. I just haven't talked about that in this particular slide. If you have that AX is equal to B, that's a matrix equation. To get X by itself, you cannot divide by A, because division with matrices we don't really have, that doesn't really make a lot of sense. And so what we want to do is get X by itself by canceling A using its multiplicative inverse. What I mean by that, I'll talk a little bit more about in the next video, but A times A inverse, they cancel each other out. You're familiar with that when you take 3 times 3 to the -1. 3 to the -1 is 1/3, and so 3 times 3 to the -1 is equal to 1, the multiplicative identity. So here, A times its inverse cancels itself out, and it's like having 1 times X is equal to A inverse times B. Now, when I multiply by A inverse, I had to do it on the left to cancel the A, so this must be on the left when you solve for X. If you enter this in your calculator, you'll use the little inverse button on your calculator, and so you could type in the calculator whatever matrix. So if this were A and it was already in your calculator, you'll simply raise that to the -1, which is a button, the inverse button on your calculator, and this represents A inverse B. So this is what your calculator screen will look like once you have those entered. If you'll press enter, then this will give you a solution. It will have a column, and it will have a bunch of decimals that look really similar to the Desmos calculator graph that I had earlier. If you'll simply press math to fraction, enter, then the calculator is going to give you 2 fractions, and again, you'll have the solution that we got before, which was x was equal to 41/11 and y was equal to 7/11. This is probably a new method for most of you, and so I do want you to practice this in the homework. In the homework, I encourage you use different methods on each problem. You want to understand each of the different methods. If one is giving you more trouble than the other, then spend some time practicing that. So here is a 2x2 system. Go ahead and pause the video. I just talked about 4 different methods. Use one of those methods. Use your favorite method and go ahead and solve this system, and then restart the video when you feel like you've had time. Okay, if you took a little bit of time to practice this, you should have gotten the ordered pair 1, 1. And so you'll notice if I substitute that back in, 2 times 1 plus 3 times 1 is equal to 5, and 5 times 1 minus 2 times 1 is equal to 3. So that point is your ordered pair. It's the intersection of these 2 lines. Hopefully you used a new method. I encourage you try substitution or matrices, or you could try graphing or elimination by addition. Try something new and keep practicing those new methods. Alright, here I have a word problem, so go ahead and pause the video. You can read it. Try to set up a couple of equations and try to solve those. Once you've taken a little bit of time doing that, we want to notice a couple things. I'm asked here to find the price of a senior citizen ticket and the price of a student ticket. And I'm given some information. Ticket sales, they sold 22 senior citizen tickets and 150, and then this was the profit, or this was the amount that they made that day. They then took in $320 on the second day by selling 17 and 50 of those various tickets. So a couple things. When you get a word problem, most students do not like word problems. We've got a lot of words there. Cut out the unnecessary information and try to highlight what's really important here. And I highlighted a couple things in color. When you see those statements from the first equation, I got that 22 senior citizen tickets and 150 student tickets came to 670. You might use different variables. You might use a different order when you write that. And that's all okay. We will come out with the same solution. So I encourage you, have you don't need to be worried that you'll get that wrong. Have some autonomy over that. I chose X as the number of senior citizen tickets and Y as the number of student tickets. You can change that. Our work may be different, but our solution would be the same. Since there are 2 sentences there that give me information, I got a second equation that looks something like this. Pause the video and rewind if that isn't clear, but go ahead and take some time to think about those. And once you've took some time to think about those, I presented one method. You could use any of the 4 methods to solve this, but here I'm talking about elimination by addition. So I wrote the first equation as it is. I noticed that the 50y here, well, 50 times 3 is 150. So what I did is I took the second equation, multiplied everything by 3, and I got this statement. Now it is the exact same equation as this equation, but it's in a different form, and it's convenient if I stack these 2 equations and add them. The 150y's will cancel. They'll immediately be eliminated. When I stack those, I'll get 22 minus 51, and on the other side I'll have 670 minus 960. So taking this row plus this row is what I'm doing there. That will give me 290 for that difference. So what I'll end up with is a negative 29x is equal to negative 290. that tells me that x must be equal to 10 and y must be equal. When I substitute 10 back in, then I'll end up with y must be equal to 3. And so go ahead and take some time, try that problem. I encourage you to spend a little time with that. This isn't given to you in equation form, and so you'll have to go from the word problem, write the equation, and that does take a little bit of practice. So take some time there, don't rush yourself, and really practice those. This represents an ordered pair. Your ordered pair might come out flip-flopped if you used the variables opposite of than I did, but that's totally okay. Those are just different approaches. So to summarize, when solving a system of equations, you could have the following outcomes. You might have one solution because they intersect. You might have no solution because they are parallel. In that case, when using elimination by addition or substitution, you might get a false statement. Something like 0 equals 5. Well, 0's never equal to 5, so you probably have an inconsistent system there. Infinitely many solutions would occur when you have the exact same information, so maybe repetition, the lines are the exact same. In that case, when you use substitution or elimination addition, you might get something like 3 equals 3. Well, that's true. If you were not able to get a unique x and y, and you're ending up with a statement like 3 equals 3, it probably means you have the exact same statement that you're plugging into itself. So in that case, you probably have infinitely many solutions. When these issues come up, please take some time to pause and try to give that thought about why you would have those kind of outcomes. Remember that you either have lines that cross once, never, or they are the same line. We've had a few different approaches that I discussed. So I discussed graphing, substitution, elimination by addition, using matrix. Use Cramer's rule and row operations. Now I believe I might add some notes about Cramer's rule, but I think I'll make that optional. Also, some of you have done this in class, you might also see things about row operations, and we might discuss that as well. So just to keep in mind, these are all different approaches you can use for solving systems of equations. Some have pros and cons. It kind of depends on your setup often, but for now, keep practicing all of these methods to get comfortable with this.